Okay, welcome back again. So we were just looking at the human capital problem. So what we have here is a parent or a couple of parents, I mean a family basically. So they have a kid and they have access to this education technology. All right, so they care about their consumption, of course, that, parents' consumption increase the utility of the parent, but they also care about their kids' education. Okay, phi is greater than 0. Why do they care about their kids' education? I don't care, right? So this is their preference. People want to give their kids, some good opportunities in life, etc. So here C is again consumption of the parent, and H is human capital of the child. Now this is the education technology. Okay. Now in this education technology, H is human capital, or this set of skills or knowledge or expertise or whatever they want to call it. Eta is a parameter, beta is another parameter, and there's gamma. Now, why do we assume that there is this additive term here? Because if you do not spend any dollars on your kid's education, your kid still have some human capital. Your kid will still have some human capital. For instance, he or she can work as a manual worker, okay? That requires the minimum amount of skills, okay? And of course, because of this additive term, then parents think about this very carefully, all right? Because even if they do not spend on the education of their kid, the kid will still have some human capital, all right? So the budget constraint is very simple. PC is consumption expenditure. E is the education expenditure for the kid. W is total income, total amount of resources that the parent can use, all right? So if you think about the Lagrange, first you should realize that you can write the utility function in this way. So you have ln C plus phi ln H, but then this is equal to phi ln eta beta plus E gamma, right? So in fact, it is ln C plus phi ln eta, okay, plus phi gamma ln beta plus E, okay? So this becomes your now utility function as a function of consumption and education. Okay, consumption level and education expenditure. Okay, then you have your Lagrange, CE lambda, this whole thing plus lambda W minus PC minus E. All right, and of course, you will find. Let me just look at the first of the condition with education, with respect to education. So you have phi gamma divided by beta plus E minus lambda less than or equal to 0. Then you have E times phi gamma beta plus E minus lambda equals 0. And then you have E greater than or equal to 0. Okay? So again, you will check what happens here, and you will find it will be equal to 0, and it will be something greater than 0 if some condition is there, and otherwise. Now, even without solving the problem, you're going to realize that, for instance, if eta is sufficiently large, let's say if eta is greater than some eta bar, this will of course depend on many other things in the model, okay, you're going to find E to be positive, okay, because education system is sufficiently productive. So it pays back, right? $1 you are spending your kid for your kid's education, and the education system is so good, it is sufficiently productive, so it is worth spending some dollars to your kids' education. All right, so I will leave that to you. Again, you're gonna find the entire characterization of the education levels and the consumption level and lambda values. Then you're gonna find the conditions that would imply that would satisfy the first order necessary condition, and then you're gonna check this function's concavity properties or quasi-concavity properties. Okay. Okay, so do you have any question about this? All right. Now let me give you one final example. Then I'm gonna, I'm gonna show you some other things about the comparative static analysis, what you know as comparative static analysis. So here's another problem. Once again, we imagine a household, okay? So there are parents, etc. So first, they care about their consumption, and then they also care about the total, let's say, quality of their children, okay? Right now, you have adults or parents' consumption, okay? Then you have fertility or the number of kids, and H is each kid's human capital, okay? Beta is positive. We can actually just a sec. Let me do even more. Oops. Let's say this is let's say psi, and this is beta, and let's put some bequest here. Okay. Now B is bequest to each kid. Okay, so phi is positive, beta is positive. All right. So what's the constraint here? Well, again, they're gonna pay for consumption. Now for each kid, there is this cost, let's say kappa n. All right, so they're gonna feed the kids, plus they're gonna send them to school, so they pay E dollars for each kid, so En is total education spending, plus they're gonna leave some bequest for each kid again. Okay, now this must be less than total income. All right, and again you have your education technology. Education technology reads eta 1 plus E gamma. Okay. So there's another variant of this problem, obviously. You can say, even if you do not give bequest with theta greater than 0, you can still obtain some positive utility. right? So there are different variants as well. Okay, so you can also solve this problem. This, I guess, would be my final example. Again, here eta greater than 0, gamma is between 0 and 1. If you are into this type of problems, you can check my website. In some of my papers, I can actually use things like this. In dynamic versions of these things, obviously, but you can still find them interesting. Of course, there are. I mean, in an optimization problem, my friend. So this is not, math for mathematics' sake. So we want to understand the economics behind all this, right? So here, how can you understand the economic intuition behind this? So what are the trade-offs? That's the question that you should ask to yourselves. Once you see an optimization problem, you want to ask, what are the trade-offs? Okay. Now, obviously, our adult agent here want to consume some goods because, let's say, she likes to go restaurants or movies. All right. So C is for her own consumption, but she also likes kids. All right. For this reason, if she has a larger number of kids and increasing, then utility increases because she also likes playing with kids. But in the meantime, she also cares about their future. Okay, so she wants to transfer some resources. One transfer mechanism here is the bequest, right? I leave my kid some bequest, some resources. It is B. Another mechanism is spending some money for my kids' education so that they could have higher human capital, so that they could earn more when they become adults, okay, when they become workers. Okay, so the trade-off here is the trade-off here is between all these components because the budget is constrained, right? So there is this total lifetime income of this parent or adult individual, which is W, and she needs to allocate these resources to these different purposes. That's the idea, basically. Okay. So you can work on this problem and to see whether you can find the entire solution. It is doable. There is a solution there. So I know that, but it's a bit tedious. So so you're gonna work on this. Okay. So let's take stock. Last week we started with what we call nonlinear programming. All right, nonlinear programming is a particular way of solving optimization problems. First, of course, we have to express our problem in the nonlinear programming format. All right, in nonlinear programming problems, you have an objective function. You have a choice vector x, right? These are multidimensional. So x is multidimensional. It's an element in a subset of n-dimensional Euclidean space. All right. So your function, your objective function, has more than one argument, and it is defined on this subset. All right. Then you have non-negativity constraints. Okay. This can be put over all of your choice variables or some of them. Okay. In some problems, you can say, okay, the first choice variable will always be positive. You can say that to consumer or the firm or the decision maker more generally. But for some variables, at least for one variable, that's the part where nonlinear programming matters because, I mean, that's the reason. For at least one variable, you will have some non-negativity constraint. And in the meantime, we're going to have our resource constraints. So these are inequality constraints. And to be more general, we usually allow people to waste resources, okay? Because sometimes their preferences will allow that. In some strange problems, that could be the case. All right? So the problem, again, has an objective function, some choice variables, some inequality constraints, and some non-negativity constraints. Then you form the Lagrange. Then you find the first order necessary conditions. You write down first order necessary conditions, and then you find a choice vector and a Lagrange multiplier vectors, a Lagrange multipliers vector that satisfy these first order conditions. You're going to solve this system of equations and inequalities. Okay? After that, you're going to check whether your objective function and your constraint functions are concave or quasi-concave, and then you additionally check some other constraints to make sure the solution candidate you found in the first order necessary condition is actually an optimum. Okay? Then you're going to go home. That's it. Let me remind you one thing. Not all problems have solutions. Okay? Sometimes there is no solution to the problem. That could be the case. All right? So in your exams or in your assignments, I give you problems and I say, find the solution if a solution exists, or prove that there is no solution if a solution does not exist. All right? I will not show you, I will not give you, okay, this problem has a solution, definitely, and you should find it. No, it's not the case. You're going to realize after checking first order conditions and second order conditions, you're going to realize whether the solution exists or not. Okay? Now, I can answer your questions. I can respond to your comments if you have any about nonlinear programming. Again, the good side of this thing is that once you invest in this type of knowledge, once you learn how to solve nonlinear programming problems, then you can solve an extremely large majority of economic problems. Okay? All right. I'm waiting for a response to your questions, comments, anything you want to share. If I left something unclear, it's the time. Okay, everybody's happy. Then let me show you a couple more things regarding these issues, and then we end this session. Okay. So when I write the problem, so up to this point, I've written the problem in this way, right? Maximize f of x by choosing x from S, subject to g of x greater than or equal to 0 and x greater than or equal to 0. Now, I want to do something different. I mean, the same stuff, but I want to express it a little bit differently. Imagine that I go specific with the parameters of the model. Okay. Let me use beta here and subject to gamma. Okay. Now here, beta is a parameter vector, let's say of dimension k, let's say k1, and gamma is another parameter vector of dimension k2. All right. So then I define alpha as a partition vector, which is an element in this Euclidean space. All right. Now, if you find the solution of this problem, of this problem, if you find the solution to this problem, that solution will look like this. X star equals some function x of alpha and lambda star some function of alpha, right? Then you're gonna ask, only after this, and of course, you're gonna check first order necessary conditions, you're gonna check second order sufficiency conditions, and you're gonna realize this is your solution, okay? Then you're gonna start asking your comparative statics exercises. Alpha, let's say J. Okay. So there are different ways of doing that, and it's a kind of a methodological issue. Now, if your purpose in developing this problem is to understand that, okay, sometimes you don't have to solve the problem, right? Because we have what we call implicit function theorem, okay? Now, let me show you very quickly what it means. So suppose that you take the first of the conditions, all right? Now suppose that those first of the conditions, and let's go reverse. First, suppose that you check second order sufficiency conditions for imagine that globally your function is concave, your constraints are concave, so theorem 2 applies, all right? Then you find your first order necessary conditions, and imagine that they are expressed in this way. So you have one condition, okay, that associates x1, x2, ... xn with alpha 1, alpha 2, ... alpha k. All right. K here is k1, k2, and this is 0. Then you have another condition, again, x alpha equals 0. Then you have another one, and that goes on. Obviously, you're gonna have this, all right? Something like that. Or let's say some of the variables are 0, then you're gonna have some, of course, inequalities, right? Then you're gonna have, if let's say x2, sorry, if let's say x3, x4, and x5 are equal to 0, you're gonna find inequalities for them, and then you have x1 star, x2 star positive. For them, you're gonna have equations. All right. Now, the idea of the implicit function theorem is this: if you have this system, so f here is from R n plus k to Rn, obviously, right? I have n equations, n unknowns, and k parameters, because my inputs are there, my arguments are there, x and alpha. Then, if the Jacobian matrix, is not degenerate, so you can check the text. So you're gonna look at the first order derivatives here, and you're gonna look at some point. You're gonna imagine that at some particular point, those derivatives exist, so the determinant is different than 0. Then eventually you can claim that there is an implicit function like this. Okay, so even without solving this, you can actually find things like that. Okay, at least you can find signs of these things. Okay, most of the time you can find the magnitudes as well in terms of partial derivatives of f and g's. Okay, you have an objective function, you have a constraint. Your model depends on the partial derivatives of these things, right? So this could be expressed as functions of these. Okay, you can check chapter 2 or chapter 3. I think it is in chapter 3. One last thing is the envelope theorem. So in a problem like this, okay, in a problem like this, g of x gamma greater than equal to 0 and x greater than equal to 0, you have your Lagrange, right? Your Lagrange is fx beta plus lambda g of x gamma, right? The envelope theorem tells you this. If you are interested in the effect of some parameter, okay, on your objective function, so again, define alpha in this way, okay, let's say alpha j, then this is equal to this is equal to that. Okay, this is envelope theorem. Again, it is expressed. Explained in your text. So let me show you one example with this. We have less than 10. So here's an example. So an income. Imagine an income problem. You have two goods. Right? Let's say beta and alpha. You have two prices. You have income, right? So the Lagrange of this problem is C1, C2, lambda, beta ln C1, alpha ln C2, plus lambda W minus P1, C1, P2, C2. Now, if you find lambda star, then this is true. Okay, you can actually prove it. So this is a very important property. If you are going to do some proofs, if you're going to use mathematical economics in your research, it is sometimes very helpful. It saved my life, as I always tell my students at this point of this lecture. It saved my life during the qualifier exam in my PhD years. Okay, I mean the problem was so difficult. I couldn't understand what's going on. It was a lottery problem, I guess, something like that. So eventually, I kind of realized that the envelope theorem, applies and saves my life. Okay. So now I stopped. We have about 7 minutes. So I can answer your questions. I can respond to your comments. I can go over the material if it is unclear for some reason. Otherwise, I will see you next week. On Wednesday, again, at 1 p.m. Oğuzhan bir şey mi dedin? Seni duymadık.
Hocam envelope teoremin üzerinden çok kısaca tekrar geçebilir misiniz?
Tamam,
O örnek üzerinden.
Orayı biraz hızlı geçtik. Zamanı yönetmeye çalışıyorum bir yandan. Okay. So let me go one slide back. So sometimes, I mean, not sometimes, most of the time, we are interested in things like that. Okay? This is why we basically, I mean, create models, right? Or things like that. Okay? So we want to understand the signs and the magnitudes of these derivatives. Okay? Now, envelope theorem tells me that the effect of a parameter, this could be any parameter in the model. It could be price, cost. Remember the parameters that we studied for these examples, right? Gammas, betas, thetas. The effect of this on your objective function at the optimum, okay, will be identical to the effect of this on Lagrange. Okay, because understand what Lagrange is doing. Remember your constraint? For each j, you have lambda j, g of j x equals 0, right? Sorry. This is the intuition. So this is always true, right? Because this is first order necessary condition. It is necessary for optimum, right? So either lambda j is positive and g is 0, or lambda is 0 directly, right? So this part, in the optimum, it basically drops, right? Then in the optimum, these functions are identical, so the partial derivative with respect to one variable is identical. So why is that helpful in microeconomic theory? Well, it is helpful. I'm just gonna share. There's a problem. Okay. Why is that helpful? Because lambda star in such a problem is linked to W itself. You see? It is the shadow price of your resource. Okay? So it basically measures the effect of 1 unit of increase in, let's say, W, this is your resource here, on your welfare. Okay? Because what you are doing here is that, of course, okay, here is the idea. I was so fast, so I forgot that. So this function, your indirect utility function in such a problem, is a function of what? Prices and income, right? So this is actually also equal that. All right? I mean, this is just the definition of the value function. This one is V. Okay? So indirect utility function tells you that as long as the consumer optimizes, you can understand the effect of these parameters, right? Directly on your welfare. Because this is, again, you start. Right? This is something you studied in your micro classes. So for the resource, you find the effect as lambda star. Was that explanatory? Once you start solving problems, you're going to understand why this lambda times G matters. Okay, because at each inequality constraint, there is always a resource. It could be time, it could be income, it could be some other resource. Okay, it could be, for example, the total amount of calories your dietitian allows for you to take. Okay, there's always a resource there. Then the Lagrange multiplier basically measures the shadow price, the value of this resource to you, the marginal value of this resource to you. Okay. All right. Is there any other input or question? We have less than a minute, so it's about to end. If you have questions or comments, I'm going to log in back again. If there's nothing, I will see you next week. Okay, so very quickly, next week, we're going to start studying dynamical systems in continuous time. Okay, please check the syllabus and look at the text. I'm gonna use Takayama for this part. It would be better if you become familiar with the material before the class. Okay.
Thank you.
Okay.
Okay. All right. Then see you next week.
Bye. See you.
Thank you. See you.
But you can always direct me your questions by email, by the way. Okay.
Okay.
All right.
Okay.